Today is Friday the 13th. Now just to let you know, the last time we had a Friday the 13th,
It was
it was the last day of school before we shut down for COVID.
Come on, baby.
Hey, you know,
And we're meeting today to discuss the future of how we're going to do things.
well, I'm sorry, but if I don't get to have another softball season, I'm literally gonna die.
I know.
Because it's so unfair.
I know, because you guys are so good.
Yes.
Okay.
We are.
So listen, hey, let me have your attention. Yesterday, we went through quantum numbers and I thoroughly got you confused. Okay, which is, happens every year on day one. Day two is to kind of rehash, finish it up, and show you that practical application of it. And then things make a little bit more sense. Okay? So, this is kind of what we talked about yesterday. Erwin Schrödinger, okay, he used math. He treated the electron as a, what? Well, that's what he called it, but he treated, Schrödinger treated, all of his equations treated the electron like a wave, not a particle. Okay? Bohr's equation was treating it like a particle. Schrödinger took the idea of de Broglie, matter waves, and treated it like that. Like Bohr's model, the quantum mechanical model has specific energy levels, or, you know, quantized energy levels. Yeah. Say what, Alan,
I'm lost all my space here.
we're on Roman numeral 3, page, I don't know
What's
the
the
page
second?
number.
It's blank blank.
It's like,
It's like the halfway to 3/4 of the way through.
Always has specific.
we have all that.
Specific, or you can even say quantized.
Okay.
Quantized means specific amount. In other words, they have set energy levels. They go first energy level, second energy level, third, fourth, fifth, sixth, seventh. But unlike Bohr's model, the electron does not follow an orbit, but rather it travels in very complex, what do we call these shapes? Orbitals. Okay? Orbitals.
Specific.
Okay? Electron does not travel in an orbit, but rather in an orbital. Most probable, it's defined as the most probable place to find an electron. Can be thought of as a blurry cloud of negative charge. That's kind of like a fan. The blade is everywhere. When I was, I think it was 8th grade, 7th or 8th grade. Back then, teachers could smoke at school. Okay? And in the teachers' lounge, they were all going there and smoke. And they had this exhaust fan, this little aluminum exhaust fan. And I was pretty convinced that in that fan spinning around, if I timed it just right, I could get a sweet tart to go through that fan and hit a teacher. Okay?
Possible.
Yeah, that's how a 7th grade brain works. 7th grade boy brain. You know, right now, it's probably what it said. So I threw it in there, and of course it then, and it was all aluminum, and it rattled around in there, made it all kind of god-awful noise and whatever. So my friend Rick and I, you know, we were on the side of the building. It was lunchtime. He took off to the back of the building, but I said, I'm going to go to the front because that's where all the kids are, and I'm just going to blend in. Well, in doing that, I ran right in front of the window of the teacher's lounge, and so I did get paddled for that. Okay, so.
For throwing a sweet tart?
Yeah.
No, that's dumb stuff.
I'm telling you, it was a different day back then. We had discipline in school. I still remember 8th grade basketball coach, Mr. Dunker. Me? No, here. That's pretty funny. All right. The point is, though, is that it turns out that that fan blade was everywhere like at once because it's traveling so fast. Okay? That's what the electron cloud looks like. The electron is buzzing around in here so fast, it looks like, you see those fast reflexes right there? Okay? It looks like it's everywhere at once, but the reality is it's just following this complex wave pattern and kind of going through, you know, it's in this area 90% of the time. Okay? So, Yeah, the electron cloud is most dense where the probability of finding an electron is high, and least dense where the probability is low. So when we look at now I'm going to get deep on you right now. Oh, it's wrong book. Wrong book.
They're fun. I have to bring my own backpack, because, you know, I'm babysitting for like, make some money. Oh, my tutor got canceled because they died.
All right. This is going to be how we figure out electrons. All right. You ready? Breathe. Take all this in. In Schrodinger's very complex math equations, he came up with an answer called the wave function. Okay? So when you plug in n, l, and m sub l, you plug in, you get all those values, you get this thing called the wave function. Okay? It's kind of like the solution. Now that doesn't mean a whole lot to us. But I don't understand the math. I'm just trusting that it's true. But it says that when you square the wave function in his equation, you get a probability of where the electron can be, might be. And in a complex equation like his, there's multiple answers. Now sometimes, you know, when you do the quadratic equation, you get 2 answers for x. Well, in his, he gets multiple. This does not represent a bazillion electrons. This represents 1 electron in the possible places it could be based upon the math. Okay? So where it's most dense, this is electron density math. Okay? Where it's darkest, that's the greatest probability of where the electron, with that given amount of energy, this is the most probable place to find an electron. Notice it can still be out here some of the time, but we draw the shape and say the shape of this orbital based upon where there's a 90% probability of finding the electron. And we're going to call this one a p orbital. It's going to look like this. Okay? Because we're going to have the greatest density here, greatest density here. That's why they kind of call it a dumbbell, because you can kind of see the two things with just kind of in between. The nucleus is right there. Okay? So when they do that for all the different orbitals, this is a 2p orbital, a p orbital on the second energy level. Okay? So again, we're getting these shapes all based upon the math, which Schrodinger got as the solutions to that complex math. But it's all just a probability, because Heisenberg says that we can't know the position and energy at the same time. We can just get a probability of where we can find it. It's all math and all probability. Our whole atomic theory is math and probability. Just to make you feel better, Einstein went to his grave disagreeing with the theory and thinking that this is crazy, there's no way an atom can be just a probability, just a math equation.
So we're partially as smart as Einstein.
Well, I'm just saying is that, I mean, it's a confusing, complicated thing. Here, on this page, these are your D, these are 3 of your D orbitals. Again, electron density, when you plug in the math for n equals 3, L equals 2, and m sub L, these are your different values. So you can see that this one is this one. Okay? We need to put a shape to it to give it a little more concrete so we can kind of see. So it's going to be here, but the 90% probability is still going to be, there's no barrier, there's no wall holding that electron in. This is just where the electron is going to be, most probably, based on the map. Okay? But that's how we're getting these shapes. All right? That's important. Electron density maps. Okay? And then we draw these shapes to kind of match up with what the experiment shows us. This one, that's your donut. That's this one right here. Got the top and the bottom, it's got the little ring around the center. All right. So, that's how we get the shapes. That's what we're talking about. this is saying right here. The electron cloud is most dense where the probability of finding the electron is high, least dense where the probability is low. And we draw a surface to where 90% of the time we have a probability of finding the electron in that space. Okay? Now, it just gives us a useful picture. It's not a barrier containing the electron, it's just the space around the nucleus. It's just the space around the nucleus where an electron most probably will be found. A space around the nucleus where the electron most probably can be found. So, our four quantum numbers. What does n, the principal quantum number, tell us? The energy level. The energy level of the electron. So n is going to equal 1, 2, 3, 4, 5, 6, or 7. It's going to be a counting number 1 to 7. Now, the maximum number of electrons, and you can just plug this in here, the maximum number of electrons is always going to be 2n squared. So on the first energy level, n equals 1, that means it's going to equal 2 electrons. N equals 2, it's going to equal 2 times 2 squared is 4, so you can have 8 electrons. So notice on the first row of the periodic table, you only have 2 elements, hydrogen and helium. On the second row of the periodic table, you have 8 elements. Okay? Now, we'll find that n equals 3. 3 squared is 9 times 2 is 18 electrons. So, now on that third row, you only have 8 columns, but we're going to find that this really is part of the third energy level. Okay? So it ends up being 18 total. And then just each time you go up, it gets more and more. But we're going to learn how to do this a different way as the day progresses. Okay? So this is all n. That's our first. Then we go to L. Azimuthal quantum number. What can it equal?
N minus 1.
So what?
N minus 1.
0 up to n minus 1. Okay? L can equal, so when L equals 0, we said that that's an S. This is all review from yesterday. L equals 1 is a P. L equals 2. And then L equals 3. Does anybody remember what it would be if L equals 4?
Was it
G. Okay, then it went alphabetical after that. That was kind of, they're theoretically possible, but practically never used. So we don't really have letters for them. Okay, but remember these refer to sharp, principal, diffuse, and fundamental. And so those are just from the colors of light when they go from different sublevels. Okay. So, only possible on this is on the first energy level and above. Okay? The P, how many P orbitals are there per energy level? We did that yesterday. How many P's were there? 3. PX, PY, and PZ, right? 3.
Would you say for B and C?
Here?
Yeah.
There's nothing on D. C here?
Yeah.
Only possible orbital on the first energy level.
Oh.
Because n equals 1, L can only equal 0.
How many S's are there?
Only 1. Oh, there's a space there. There's only 1 right. I didn't see that space. There's only 1 S. So there's only one way a sphere can be oriented in space. Okay? This does not want to stay in that space. 3p orbitals, how are they arranged to one another? They're all going to be what? They're on the x, y, and z. Math term. Perpendicular to each other.
Oh, yeah.
Oh, yeah. X, 90 degree perpendicular. So they're all perpendicular to each other, 90 degrees in x, y, and z axes. Now, they only exist on the second energy level and above. Because in order for L to equal 1, N has to equal 2. So you can't have a P sublevel until the second energy level. So if N equals 1, L can only equal 0. If N equals 2, L can equal 0 or 1, because both are equal to or less than let's just leave off, just scratch through the because part. So, N equals 1, L can equal 0. It's always 0 up to N minus 1. So this is telling me the sublevels. So on the second energy level, there are two sublevels, S and P. And S orbitals always have lower energy. We'll maybe talk about that today, if not for sure on Monday. S orbitals always have lower energy than P orbitals. Same energy level, but it's a sublevel. It's just a little stair-step difference in energy. And the energy of an electron in an orbital is how tightly held it is to the nucleus. The lower the energy, the more tightly it is held to the nucleus. The more energy it gets, the farther away from the nucleus, the less pull the nucleus has on it. Okay? So you always have to say, when you say lower energy, you might want to put a little right underneath that and say, more, held more strongly to the nucleus. Held more strongly to the nucleus.
The L, the S, or the P?
The S. The lower the energy, the more strongly held it is to the nucleus. All right, we got to get to the practicality here. But I got to get you to have all this filled in. Okay? L equals 2 is the D. How many D orbitals are there per sublevel? 5. Okay? But in order for L to equal 2, what was N equal? 3. So only exists on the third energy level and above. So if N equals 1, L can only equal 0. If N equals 2, L can equal 0 and 1. So on the first energy level, you have 1 sublevel. On the second energy level, you have 2 sublevels. But if N equals 3, L can equal 0, 1, and 2, meaning we can have all 3 sublevels. So again, this is a 1s, this is a 2s. What's a 3s going to look like?
It's bigger than that.
A bigger sphere that's going to encompass this. So as we do our Russian doll thing, okay, we just put this bigger sphere over this one, and then this one goes over this one, and the nucleus is in the center of all of them. Same thing with the P's and the D's. They just get the same shape, they just get bigger and encompass the other one. Then they have a space in between, a nodal region where there's a low probability of finding the electron. Electrons are going to be dense here, not dense in between, dense on the next energy level, space in between, next energy level just get bigger and bigger. But the shapes are all the same, these 4 different orbitals, S, P, D, and F. And S is always spherical. The P's are always this dumbbell shape. It's just the 3P is bigger than a 2P. A 4P is bigger than a 3P. All right, now, on the third energy level, so then on the third energy level, there are 3 sublevels. What goes in here? S, P, and D. And D orbitals have more energy than P's. What does that mean about D orbital? Electrons in a D orbital compared to electrons in a P in terms of how strongly held they are to the nucleus.
The D ones are less.
The D's are less strongly held. Higher energy means less tightly held. Finally, we get to the F's, very complex shape. How many F orbitals are there? We got one, now look at the trend. 1 S, 3 P's, 5 D's, 7 F's. Hopefully that's not what your report card looks like. All right, so this is where we ended up though, on the magnetic quantum number, M sub L. It's how we know that about the 1, 3, 5, and 7. What can M sub L equal?
Negative
Negative M
and to positive.
to positive M. So M sub to negative L. Negative L to positive L. So if L equals 0, what can M sub L equal? 0. L equals 1, M sub L equals
Negative 1, 0, 1.
-1, 0, and 1. So this is your S. Only one possible answer, so there's only one orientation in space. This is your P. 3 answers, 3 orientations in space, Px, Py, Pz. We have 3 orbitals possible on the P sublevel. L equals 2, which is your D. What can M sub L equal?
Negative 2, negative 1, 0, 1, 2.
How many answers is that?
5.
5 answers, therefore how many orbitals are there on the D sublevel?
5.
5. And then when L equals 3, which is your F, M sub L is going to equal -3, -2, -1, 0, 1, 2, and 3. How many answers? 7. So we have 7 orbitals. So how many, with L equals 4, which is the theoretical G, how many orbitals would there be on the G sublevel?
9.
9. Okay? It's all math. It's all just, all based upon limiting the energy of the electron. This quantum theory. Okay? So if L equals 1, M sub L can equal from -1 to +1, or -1, 0, and 1.
Can you just put like absolute value of that number? One of them.
Well, because you got to include the 0.
Or in.
So, if L equals 0, M sub L can only equal 0 up to n minus 1, or M sub, this really, that one's not as important as this one. It can only equal 0. Here it can equal -1, 0, and 1. Okay?
Wait, so Mr. Hobbs, where it said only one value for M sub L, blank means there is only blank orbital in the S sub L.
There's only one. One answer, one orbital. Each value of M sub L corresponds to a different orbital. Just a different orientation in space. Fancy word. We call them degenerate orbitals. Degenerate, and I don't know how they get this meaning of the word, because if I hear the word degenerate, I think of somebody that's not a, good person, or, they're a weight on society.
I think of Ellis because it sounds like degenerate.
Okay, but degenerate in this case means equal energy orbital. Since there are 3 possible values for M sub L when L equals 1, there are how many orbitals? 3. Each value of M sub L corresponds to a specific, it really needs to say orbital. Cross this out, cross this word out and put orbital. I miswrote that one right there. Now this is what I was just saying. All orbitals within a sublevel have equal energies, just different orientations in space. Px, Py, Pz. Equal energies, just different orientations in space. So if L equals 2, what can M sub L equal? -1, 0, 1, and 2, right? 5 values means there are how many orbitals on the D sublevel? 5. And then when L equals 3, M sub L can equal -3 all the way through. 7 values means 7 orbitals. Okay, we're almost there. We're almost about to put the pieces of the puzzle together and actually see a picture. Our 4th and final quantum number.
Spin.
okay, is the spin quantum number. It can only equal plus 1/2 or minus 1/2. Can only equal plus 1/2 or minus 1/2. And it's all that means, and the 1/2 is meaningless. It just means that it's spinning clockwise or counterclockwise. Electrons are negative, so they're going to repel one another. The only way they can be in the same space is if they have this opposite spin. It kind of gives them a different magnetic field as they're spinning in opposite directions. So it helps them to not repel as much. It allows them to occupy the same space. That's known as the Pauli exclusion principle, is you can only put 2 electrons into any orbital. You only have 2 choices, plus 1/2 or minus 1/2. Only 2 electrons, and they must have opposite spins. Okay? Now, by knowing the 4 quantum numbers, N states the energy level, L states the sublevel, M states the specific orbital, and M sub S states the spin. Energy level, sublevel, specific orbital, spin. So we have our hotel orbital. It's a crazy looking hotel. We haven't fun yet? Woohoo! Yeah. Okay, we're going to get to what all this means. So here's my nucleus. So the electrons are going to start being added to this nucleus. The nucleus is positive, but where do the electrons go? They can't just go anywhere. We've realized that the electron has to have fixed energies. There's only certain distances that it can be from the nucleus, these energy levels. And even in those energy levels, according to Schrodinger's equation, they're traveling in these complex wave patterns in these orbitals, these places around the nucleus. So the electron's kind of subdivided on where it's going to be. It looks like a big just sphere of electrons, but they're really a little bit more method to the madness. So if I have my first energy level, I have my S orbital. That's the only sublevel, so it's hard to have a sublevel when it's the only one, but that's all we have on the first energy level. And how many electrons can be in that?
2.
Just 2. And they're buzzing around in some kind of wave pattern there. Then we go to the second energy level. On the second energy level, what sublevels are possible? S, which is going to be a bigger sphere. Okay? And how many electrons can be in that one?
8.
Just on the S, again, only 2. We're getting to why you have the 8. Okay? Now, we also then, on the second energy level, have what sublevel? P, right? L equals 0, L equals 1. The P's that... Let me cap on. Yeah, I didn't call back though. There's 1 P. How many P's are there? How many P orbitals are there on sublevel? 3. PX, that's PY, PX, and PZ. And there's going to be 2 electrons in each one. Now, the electrons are not confined. This is not a specific place, but this is the general probability. If you put in N equals 2 and L equals 1, there's a good chance you're going to find the electrons in one of these spaces, a 90% probability or better. Okay? So that's what this actually looks like. So 10 electrons is 10 protons, that's neon. That's what this picture is right here. Okay, you have the 1s orbital with 2 electrons in it. You have your yellow 2s, that's bigger, encompassing it. Then you have your P sub P orbitals, all perpendicular to each other. So if we looked at neon, we're going to see that there's 10 electrons. But those 10 electrons aren't just going anywhere. They're in very specific places based upon their energy. This entire periodic table is arranged based upon these orbitals. The chemicals react in certain ways because of these crazy orbitals. Okay? So I know it doesn't make a whole lot of sense, but That's just the way it is. So now we go to the third energy level. Okay? So what sublevels are possible on the third energy level?
S, D, D.
Okay? So I go to my third energy, a bigger sphere. Notice I have this nodal region in between where there are no electrons, or a very low probability of finding an electron. So I'm going to have the bigger sphere. Still only 2 electrons in it. What else can I have? A bigger P's, right? Okay, and so we can put 2 electrons in each one of those. I think I got them all. Okay? Then, in addition to these, what else do we have? No.
S and D.
D. Okay, we have the S, the P's, and then the D's on the third energy level. Now, I'm not good enough to draw all these D's. They're too complicated. Okay, but we would superimpose all 5 of these d orbitals. Okay, this is number 5. We'd have to draw all those onto here. And even though these are much bigger and more complicated, there's only 2 electrons again in each one. It's a pretty complicated model. But our quantum numbers, what we do then is we can just say, we can do what's called an arrow diagram. So on my first energy level, I only have 1 orbital possible, and it's an S orbital. And we're going to go increasing energy. On my second energy level, what do I have? What sublevels are possible on the second energy level? S and P. So I have the 2S. And then remember, the P's are slightly more energy, so I have my 2P. So, but I have 3 of them. And then I go to my third energy level. What do I have? S, P, and D. And D's are even more energy, and there's going to be 5 of them. So if I want to put electrons in, I want to see how our electrons are arranged, say in magnesium, element number 12. Okay? I know I can only put 2 electrons into any one of these orbitals. The Pauli exclusion principle, you want to know about price for this one too. Okay? In other words, these guys are pretty smart and they figured stuff out that most people couldn't figure out, so that's why your brain is hurting right now. Great. So I use an arrow. An up arrow is the positive 1/2. A down arrow is that negative 1/2. My first energy level is filled. Notice 2 electrons, that's helium. This is what helium's electrons are going to have. 2 electrons in this 1s orbital down here that's buzzing around. But that's all that the first energy level can hold. So we've got to go to the second energy level. Okay? That second energy level, 1, 2. Notice on the periodic table that's kind of divided up, there's only 2 columns in that first section. Right here, lithium and beryllium. That's the electrons going into the 2s. Okay? Then we jump over from 4 to 5. Notice we jump all the way over into this other section, which is going to now be my 2p section. Now when I'm putting electrons into the 2p, I'm going to go 1, 2, 3. And at the bottom of your notes there, it talks about the 3 rules that govern the filling, and this is known as Hund's rule. Hund's rule. You put 1 electron into each orbital and they must have the same spin. And well, I don't have time to get into it today, but just know that all magnetism, the reason why the magnet sticks to the refrigerator is because of Hund's rule and the fact that you have all the same arrows. It's all up arrows on the North Pole, it's all down arrows on the South Pole, they all stay, and it's because of the electrons spinning on their axis on the same direction why magnets stick to a fridge. Hard to believe, little tiny electrons spinning is what makes a magnet, but it is.
The more I sit in this class, the weirder and weirder Earth seems.
The more and more amazing it seems.
No, it's just weird.
Okay? And this electron that we can't figure out, so that electron that's spinning on its axis, sometimes it acts like a particle, sometimes it acts like a wave. It's a wave until we look at it. If we look at it, it acts like a particle. Okay? It's kind of like, you know, what are those movies where the dogs, you know, they or whatever, they can talk when the people aren't around, but you know, even like Toy Story, you know, they can talk when the people are around, but when the people are there, they're just normal toys. That's kind of the way the electron is. It's a wave until you look at it, then it's a particle. It's crazy. Okay? So, then we fill it up. That's, how many electrons are there now?
There's 8 on the.
There's 8 on the second energy level, right? 10 total. This is neon. Neon's going to have 2 electrons in an S. 2 more electrons in the 2s. It's a bigger sphere. Then you're going to put 2 electrons into each of the p sublevels here. They're all superimposed on one another, so it just looks like this chaos of electrons, but the reality is, based on the energy, there's a specific place they're going to be. So now I go to my third energy level. So now I go 11, I have 10. Notice I'm now the second energy level is filled, isn't it? Neon, where is it located on the periodic table?
Noble gases.
Noble gases, but the end of the second row, right? When you go from 10 to 11, you start a new row. Because I'm going to start a new energy level. So, magnesium, 11, 12. It's going to look like that. Notice that hydrogen has 1 electron in the one electron in the 1s. Lithium has 1 electron in the 2s. Sodium has 1 electron in the 3s. As a result, since they have the same outer shell electron configuration, lithium, sodium, and potassium, rubidium, they all have the exact same properties. They react the same way. They all kind of blow up in water, which we'll see later on next year. So we just keep building this. So if I want to look at my 4 quantum numbers, the quantum numbers, if I go to a hotel, and I get a room key that says 2435, and this is a big, tall hotel, what does the 24 probably tell me? Yeah, I'm on the 24th floor. Then when you get off on that floor, there's going to be signs saying rooms 1 through 10 are this way, 11 through 20 this way, 21 through 30, you know, right? Down to each different hallway.
This is a massive.
Okay? And then once you get into the hallway, each hall has a different number of rooms with a room number. And the hotel rooms have a maximum capacity. Our hotel rooms have a maximum capacity of 2. Okay? And because nature's way, they're going to have opposite spin, plus and minus. And of course, they would be married if they're in a hotel room. And so, okay? So, N tells us the floor we're going to. L tells us which hallway we get off onto, which sublevel. M sub L tells me which room I'm in on that sublevel. And then the spin tells me, you know, am I the guy or the girl? Plus 1/2, minus 1/2. So you decide which one's which.
It goes in this floor.
Okay?
L is hallway.
M is the room. Okay? So if I look at this electron right there, I'm going to say N, it's on the second energy level. Right? L, when N equals 2, L can equal 0 and 1. But since it's on the P sublevel, which value of L does that correspond to? Which value, 0 or 1, corresponds to a p sublevel? 1. So L is going to equal 1 here. M sub L, if L equals 1, what can M sub L equal? Negative 1, 0, and 1, right? Negative 1, 0, and 1. That's my M sub L. Specific orbitals. Which room in the hotel are we in? So this one's in which room? 0. Okay, we're going for that electron right there. It's in 0. And since it's going down, M sub S is going to be minus 1/2. This is the quantum code. Based upon that energy, we know the electron is going to be in a p sublevel on the second energy level in one of the orientations, a specific x, y, or z orientation in space. That's what our quantum numbers tell us. Okay? But the quantum numbers, you have to understand, were all developed to explain the observations that we see on how things can transition from one sublevel to another and get all these lines. Okay? Well, let's look at, if I look at this electron then. This is electron 1. This will be electron 2. What energy level is it on? 2 again. But this time, L is going to equal?
0.
How do I know it's 0?
Because it's not going to be.
Because it's in the S sublevel, which always corresponds to L equals 0. L equals 1 is always a P, L equals 2 is always a D, L equals 3 is always an F. So, this time L is going to equal 0. Well, when L equals 0, what's my only possible value for M sub L? Minus L to plus L, minus 0 to plus 0 is only 0. Only one answer, so M sub L equals 0. And then since it's going up, plus 1/2. All right, one more. If I do that electron, this is number 3. N equals 3. L equals 0. So M sub L has to equal 0. And it's going down, so it's minus 1/2. Okay? So these quantum numbers tell us how, they kind of give us the quantum code. It lets us know where the electron is going to be. And that's our whole goal of this whole unit. Everything we learned about light and everything else is on the photoelectric effect. It's all leading up to how do we know how the electrons are arranged or configured around the nucleus. Schrodinger's equation, as complicated as it is, gave us this model that we can use for all atoms. Okay? Now, unfortunately, there's one more little wrench in the works, which we don't have time to get into today. Thank God, there isn't. Oh, thank God, it's Friday afternoon. But what happens, and we'll talk about this on Monday, what happens is that the electrons, the sublevels actually begin to overlap. Okay? Now, let me kind of foreshadow just a little bit. How many orbitals are there on the D sublevel? 7's on the F, 5 on the D. How many electrons can go into each orbital? 2. So 5 times 2 equals 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? This is where electrons fill your D sublevels. How many can go in the S's? How many orbitals are there on the S sublevel? 1, with a maximum of how many electrons? 2. 1, 2 in this column. How many orbitals are there on the P sublevel? 3, for a total of how many electrons? 6. 1, 2, 3, 4, 5, 6. And then how many on the F? 7 times 2 is 14. 1, 2, 3, 4, 8, 14. Okay? So the whole periodic table is based on that, but notice we go here, we're at P6 for argon, 3P6 is where it would be if we kept going. But instead of going into the D's, we hit the S's first. So 4S actually fills before 3D. Okay, so there's going to be some overlap of orbitals. And on Monday, I'll get into great discussion as to why and how that can be. Okay?
Look forward to it.
But then I'm going to give you a way to memorize or learn how to do it.
And the test on this is next week?
Next week.
Okay.
So I'm going to put the study guide up today. We only, I mean, if you look at the notes, you only got like this much left to note.